thank you very much for coming to this talk. This is joint work with Jonathan, where we ask, why do misspecifications persist? Right, so in a lot of economic situations, people draw misspecified inferences about the world. By that, I mean they start with a prior belief that rules out the true data generating process. For instance, there's by now a large literature in behavioral economics that documents various biases and mistakes. When people reason about an aspect of the environment under one of these biases, they're engaging in misspecified learning. There is a recent literature following Espondo and Puzo 2016 that studies the implications of misspecifications, taking these errors as exogenously given. This then raises the question of why do these mistakes that distort learning persist? This seems especially puzzling given the conventional wisdom that competitive pressure should eliminate mistakes. In this paper, we present a framework to evaluate competing misspecifications based on their objective payoffs, focusing on which misspecifications are likely to persist over the correct specification and in which environments. So here is an example to keep in mind. Suppose there are many players in a society, and they're paired in every period to play a linear quadratic-normal game. Think of the players as different firms, and think of the game they're playing as an incomplete information version of Cornell duopoly. So there are 2 players per game, and these different games that people are matched into can be viewed as different markets. In a game, nature first draws a type from a normal distribution, interpret that type as the demand state in a specific market. Each firm gets a signal about nature's type, and so signal Si is equal to the true type, the true demand state, plus some error term. After observing the signal Si, the firm then chooses a quantity to produce. A market price P is then realized as a function of the true demand state, as a function of the average production among the firms, and depending on this exogenous price shock. This parameter R here is the elasticity of market price. It tells you as the firms increase their production, how quickly does market price decrease. The ith firm gets a payoff that's equal to its production times the market price minus this quadratic production cost. Now, the parameters of the game, things like this R parameter over here, are fixed over time, but this state omega is redrawn in every game. So there's day-to-day fluctuation in the market demand. The signals of the 2 firms are conditionally correlated. By that, I mean this error term is a convex combination of 2 components. The first component, we have this eta I term, the idiosyncratic component of error, which is IID across the 2 firms. And then we have this common component Z, which is common to both firms. This parameter kappa over here in 0,1 parameterizes a conditional correlation of the signals. When kappa is 0, there's only this idiosyncratic component and the signals are conditionally independent. When kappa is 1, there's only this common component and the 2 signals are always the same. Initially, there's a homogeneous group of rational firms that know the true correlation to be kappa dot, as well as the other parameters in the game. Now imagine a small fraction of new firms enter the society. These new entrants differ from the incumbents in 2 ways. First, they hold a dogmatically wrong belief about signal correlation, believing it to be some other kappa not equal to the true kappa dot. Second, being new, they're uncertain about the parameters of the game. In particular, they're uncertain about this price elasticity parameter. But they're repeatedly playing this game period after period, and they observe prices at the end of every game. And so they can use these observations to learn this elasticity parameter. Notice that these entrants are engaged in misspecified learning, and that's because after they see their own signal, they hold a wrong belief about the rival firm signal because of their wrong idea about the correlation between the signals, and thus have a wrong idea about rivals' production level. So when they do see the market price at the end of the match, they misinterpret that market price and mislearn the game parameters. Now, will the market drive out these misspecified entrants? The answer is actually no. The misspecified entrants can actually outperform the rational incumbents and grow in prominence. Moreover, the type of mistake that can invade a rational society depends on matching assortativity. That is the social structure that determines how these new entrants are matched with each other or with the incumbents to play this game. Let me introduce the general framework before circling back to this example. The primitive environment, the objective primitive, consists of a symmetric two-player stage game where each player has a common strategy space A. There's a set of consequences Y and a utility function which maps your consequence into your real valued payoff. So these consequences are the observable outcomes that agents use to learn the game parameters. Now, in the example from before, we can take the consequence to be, containing your own signal, the quantity you produce, and the realized market price at the end of the match. Notice that in that case, your payoff, namely, your profit, is a function of that consequence. There is this objective distribution F dot, which maps profiles of strategies into a distribution over consequences. This tells us how every profile strategy translates into your own consequences. And so this F dot here is going to capture the true parameters of the stage game. Right? So in the example from before, this F dot would say how two strategies from the two firms translate into a distribution over market prices and other things, given the true signal correlation among the two firm signals and given the true price elasticity. Now, of these primitives I've introduced, agents know most of them. They know the strategies, they know the consequences, and they know the utility function. What they don't know and what they're trying to learn is this F dot, this mapping from behavior into consequences, right? So for instance, when you're uncertain about the price elasticity in that example, you're then uncertain about this mapping. A model is a map, a conjecture about how strategy profiles translate into these consequences. And a theory is a set of models. A theory is said to be misspecified if this true mapping from behavior into consequences does not belong to the theory. So you can think of a misspecified theory as a scientific paradigm based on some false premise. And so in the example from before, our entrants hold a misspecified theory about signal correlation. They don't just have a single model of the game, they have many different models contain that theory. The different models are indexed by different values of price elasticity. But all of the models contain the wrong parameter for kappa, the correlation in signal. More generally speaking, each agent will start with a persistent theory, A or B. They're going to calibrate that theory based on their experience to find the best fitting model within the theory. In each period, each agent is matched with an opponent, observes the opponent's group, whether they're from group A or group B, and choose a strategy to use in the match against that opponent in the stage game. Okay. The profile strategies generates a consequence for I from the objective distribution that generates consequences. This consequence gets observed, this determines I's payoff in that period, and this will be used by I to make inferences among the models within her theory. Now, let me introduce the concept of zeitgeist and equilibrium zeitgeist. What we're trying to do here is that we're trying to describe the social composition and interaction structure in a society with multiple coexisting theories. So in words, a zeitgeist is going to be a landscape of beliefs coming from different schools of thought. It includes the relative prominence in the society and the interaction among the adherents of different theories. So it consists of two theories, A and B, a model for each theory, the sizes of the two groups, PA and PB. It tells us about each group's behavior when it's matched. So in particular, AAB here says what strategy will someone from group A use when matched up against an opponent from group B. And a matching assortativity parameter, lambda. Right? In how this lambda works is that in every period, your match with an opponent from your own group is probably lambda, and your match uniformly at random against someone from the entire society was probably 1 minus lambda. So a higher lambda means a more assortative social interaction structure. Now, a zeitgeist just includes these, beliefs and behavior without any kind of optimality conditions or constraints. An equilibrium zeitgeist, which I will abbreviate as EZ, is like a zeitgeist with a pair of optimality conditions imposed on top of it. It is a zeitgeist where behavior, things like these, are optimal given these beliefs in the models. And conversely, the models that people believe in are the best fitting models within their theory, given the behavior. Intuitively speaking, EZ describes behavior and beliefs which will prevail among different groups in the steady state, holding fixed the population proportions. Now, I will use the idea of EZ to define evolutionary stability. Right? So remember, EZ describes how many of the people are in each group and what they're doing when they're matched with every kind of opponent. We can then compute the fitness of each theory in EZ, which is the objective payoffs of the adherents of that theory. So in the back of our mind, we have this evolutionary story, right, where theories are the basic heritable units of information. A theory whose adherents do better are going to create more intellectual descendants in the future because they have more resources. The question of evolutionary stability is the question of, can a theory A, starting at a position of social prominence, called that the resident theory, fight off invasion from epsilon proportion of a different theory B? We might call that the mutant theory. If so, we will say theory A is evolutionarily stable against theory B under the particular matching technology here. Now, let's use the definition of evolutionary stability to examine the example from before, right? So recall we have this example where people are getting these conditionally correlated signals about the state. The correctly specified theory is one where this kappa parameter is equal to the true correlation parameter kappa dot. But it turns out that this correctly specified theory may not be evolutionarily stable against theories that contain mistakes. Indeed, when lambda is 0, that is, there's uniform matching, the correctly specified theory is not evolutionarily stable against misspecified theories where kappa is slightly too high. This bias is sometimes called projection bias, where people overestimate the similarity between their information and other people's information. But if lambda is equal to 1, that is, these people are matched always within their own group, perfectly assortatively, then the correctly specified theory is not evolutionarily stable against misspecified theory with the opposite mistake, where kappa is below the true correlation. We might call that correlation neglect. So in this example, we see that the correctly specified theory may not be evolutionarily stable against mistakes, and furthermore, it is the interaction structure, the details interaction structure in terms of how people of different schools of thought are matched together to play this game. That is what determines the direction of the error, which can invade a rational society. Now, what exactly is going on here? Let me explain this result. What's happening here is that in EZ, these mistaken theories make wrong inferences about R, about this price elasticity parameter. It turns out that correlation neglect theories are going to overestimate elasticity, and projection bias theories underestimate it. Why? Imagine we have an agent that suffers from correlation neglect. Suppose that agent happens to have a large and positive private signal in this period, and they increase their own production in response to this good news. Because of correlation neglect, they don't realize that their opponent probably also has a very large and positive signal, and they underestimate opponent's optimism about the state. And so when they see that market price is low, which is actually caused by both firms increasing their production, they misinterpret that outcome, thinking that only they had a large and positive signal, only they increased the production. And from that low market price, they infer that the market price elasticity must be very high, that as I increase my production by a bit, look at how much this price has dropped. And conversely, someone who has the opposite bias, projection bias, are going to underestimate elasticity. Now, these misinferences about R, about elasticity, matter for behavior in the EZ. It turns out that firms behave more aggressively, in the sense of more aggressively increasing their production when they have a large private signal, if they believe in a more inelastic price. With uniform matching, these projection bias mutants mislearn the elasticity to be too inelastic, and that generates for them a commitment for aggressive play. When they're matched up with these rational opponents, the rational opponents yield, and the surplus division favors the mutants because of that commitment. And so that's how they're doing objectively better than the rational incumbents. On the other hand, when there's perfectly assortative matching, the correlation neglect mutants mislearn the elasticity to be too high. When they get matched with another mutant, They collude on less aggressive play, and that improves both firms' total surplus, and that's how they're doing better than the rational incumbents. Now, I want to zoom out from this example for a moment and highlight something important about our framework. In this framework, the heritable unit of cultural transmission is a theory, which is a set of models, not a single model. Which means that given a misspecified theory, learning in different environments may lead the agent to believe in different models. This contrasts with the case of preference evolution, where agents are endowed with a fixed subjective preference over stage game strategy profiles that may differ from the objective payoffs. The fact that agents are not endowed with a single fixed model, but rather endogenously learn a model from the set of models that they deem plausible, that's what we call the learning channel. And on the next 2 slides, I will give you a whirlwind tour of some of the new stability phenomena which depend on the learning channel. By that, I mean they cannot happen in the world of preference evolution. They cannot happen if people just have singleton theories. In this picture here, I am showing you the fitness of a particular mutant theory in some environment as a function of assortativity. Okay? The color lines is showing the mutant theory's fitness, and the dashed gray line is the resident theory's fitness, which is independent of lambda. What we see in this picture is that this resident theory A is evolutionarily stable against theory B, both under uniform matching and under perfect assortative matching, but not in this intermediate region where the color line goes above the gray line. And in other words, we have this non-monotonicity instability. We have non-monotonic stability in matching assortativity. This cannot happen without a learning channel. It turns out that without a learning channel, fitness will always be a linear function of lambda. And so being evolutionarily stable for the extreme points also means you're evolutionarily stable for all of these lambda. Something else which depends on the learning channel is stability reversal. We say 2 theories exhibit stability reversal if when theory A is dominant, the adherents of A get strictly higher payoff than those of B, both against A opponents and against B opponents. But also, when B is dominant, the adherents of B have higher payoff than A in expectation. So it's a strong kind of multiplicity and relative stability of 2 theories under uniform matching. It really depends on which one is dominant. And we can find examples of this, and they have to happen through the learning channel, not with singleton theories. So to conclude, we introduce zeitgeist and equilibrium zeitgeist to describe social composition interaction structure of agents with different misspecifications who are matched to play a stage game. We define evolutionary stability of a theory based on objective fitness of their adherents. We show that the correctly specified theory may be unstable against misspecified theories, and that the learning channel can lead to novel stability phenomena. The interaction structure in a society can select which errors persist, as we illustrate in a linear quadratic normal game. Thank you very much.